In class, we've been studying some theoretical derivations of confidence intervals, and the goal of this video is to just apply a confidence interval to a particular example. So let's suppose that we have a manufacturing process that produces screen protectors for iPhones, and our goal is really to estimate the true average width of a screen protector produced by this process. And so we might take a sample of 40 different screen protectors at random and measure the width. And we're supposing here in this example that we've done that and we've measured the width of the average width to be 67.3. So this is a sample mean or sample average. And we're also supposing that the standard deviation of the measurements is known to be 0.1. So here in this example, we're assuming that we have sigma to be known, which is not always the case. So our goal here is to calculate the 90% confidence interval for the true mean screen protector width. So in class, we derived a formula to do this. And the formula is x bar minus z alpha over 2 times sigma over the square root of n. So that's the lower bound, and the upper bound is x bar plus z alpha over 2 times sigma over the square root of n. So we need to figure out what these quantities are. And we can start with alpha. So a 90% confidence level implies that 1 minus alpha times 100% is equal to 90%, and that implies that alpha is equal to 0.1. And we would also need to find z alpha over 2, and in this case that will be z of 0.05, and at this point we could use a table to find this value, which I will show you how to do in class, or you can use an R function called qnorm in order to find this value. So z alpha over 2, you can use the qnorm function to find. But either of those methods will of course yield the same thing, in this case 1.64, and I guess this is really approximate equality. And so from there, it's easy enough just to plug values in. So 67.3 minus 1.64 times 0.1 over the square root of 40, and then 67.3 plus 1.64 times 0.1 over the square root of 40. And this interval, if we round a bit, we should get 67.27 as the lower bound and 67.32 as the upper bound. So depending on the goals of your analysis, we could view this as a very narrow interval or a very broad interval. It depends on how much tolerance we can allow in this manufacturing process. And as someone who might study this manufacturing process, the idea is that this so-called domain expert knows how much tolerance should be allowed. So let's think about the interpretation of this interval. And technically speaking, it's actually very hard to interpret the computed confidence interval. So one way of interpreting the computed confidence interval that might be controversial in some circles, but some view it as reasonable, is to think that the values that fall within this interval are plausible values that you can use to estimate the mean. So they're a set of plausible values used to estimate the mean. But we shouldn't say certain things like there's a 90% chance that this interval covers the true parameter, because making probability claims about a constant interval and a constant true mean mu doesn't make sense unless the probability claim is 0 or 1, right? The probability that a constant will fall within this interval will either be yes it will or no it won't. There's nothing probabilistic about it. So that kind of interpretation is clearly problematic. Now, it's easier to interpret the pre-calculated interval. So when this is a random variable, x bar is a random variable, then we can say something like, well, if we computed this interval for many, many different samples of size n, then 90% of them in the limit will cover the true mean mu. So basically, the procedure that we use to obtain the interval estimate is a reliable procedure. So it's hard to make specific claims about the actual interval that you calculated, but really you've calibrated the procedure to know that it's reliable in covering the true parameter. Okay, so quickly, if you wanted to go to the 99% confidence interval, the main difference is calculating a different z alpha over 2. So in this case, our alpha is 0.01, and we get a z of 0.005, and then this critical value is 2.57. And so we end up with an interval of 67.25 up through 67.34. And of course, this is approximate. There's some slight rounding. Now, if you compare these two intervals, the 90% and the 99%, you'll notice that the latter, the 99% interval, is wider. And so I think that should make some intuitive sense. As you increase your confidence level, as you say, I'm more confident in the calibration of this interval covering the true parameter, for the same sample size and same assumptions about a random sample, etc., you should see a widening of the interval. If you get more confident, you should broaden the range of values that you're considering. So that's a general rule. It's true that for all things equal, increasing the confidence level will also increase the size of the interval, meaning the length of the interval. And so that sort of gets at part C. What are the advantages and disadvantages to a wider confidence interval? Well, a wider confidence interval will have a higher confidence level associated with it. So you can be more confident in your interval because you know that the procedure that generated this interval covers the true parameter more often than the procedure that generated this interval. So that's an advantage. But a disadvantage is that, well, of course it's wider. And so in part A, you're saying the range of plausible values are between 67.27 and 67.32. And with a higher confidence level, you're saying that there's a larger range of plausible values.